To obtain 120/208 single-phase power, you have two primary options. Firstly, you can use a transformer to step down the voltage from an existing 120/240 single-phase supply, or secondly, you can install a completely separate electrical service dedicated to the equipment needing this specific voltage. Let's delve into each option. The first option involves using a transformer. A transformer is an electrical device that transfers electrical energy between two or more circuits through electromagnetic induction. To utilize this, you would install a transformer that is specifically rated for a primary input of 120/240 volts and a secondary output of 120/208 volts. This transformer will take the existing 120/240 volt single-phase power and convert it to the required 120/208 volts. The 120/240 volt supply is connected to the primary side of the transformer. This is the input side where the existing power source is fed into the transformer. The equipment, such as an X-ray machine, is then connected to the secondary side of the transformer. This is the output side, which now provides the required 120/208 volts. It is critical to ensure the transformer is properly sized. The size of a transformer is rated in volt amps, often expressed in kilovolt amps or kVA. The kVA rating of the transformer must be sufficient to handle the load imposed by the equipment. To determine the appropriate size, calculate the total volt amps required by the equipment and then select a transformer with a kVA rating that meets or exceeds that requirement. Consulting with a qualified electrician is crucial to correctly size the transformer, accounting for factors such as inrush current and future load expansion. The second option is to install a separate electrical service. This involves running a new service drop from the utility pole directly to a separate electrical panel. This panel will be exclusively dedicated to providing power to the equipment. A new meter is installed to measure the electricity consumption of the separate servers, and a breaker is installed within the panel to protect the circuit from overloads and short circuits. The equipment is then wired directly to this new panel, which will supply the required 120/208 single-phase power. This approach ensures that the equipment has a dedicated power source, isolated from other electrical loads in the building. When considering these options, several factors should be taken into account. Firstly, safety is paramount. Transformers must be installed according to all applicable electrical codes and regulations. Proper grounding is essential to prevent electrical shock hazards. Overcurrent protection, such as fuses or circuit breakers, must be installed to protect both the transformer and the connected equipment. All electrical work should be performed by a qualified electrician who is familiar with local codes and safety standards. Secondly, there is the cost to consider. Installing a separate electrical service is typically more expensive than using a transformer. The cost includes the new service drop, the new meter, the new electrical panel, and the associated wiring and labor. However, the long-term operating costs may be lower with a separate service if the equipment consumes a significant amount of power. A transformer continuously consumes a small amount of power, even when the equipment is not in use. Thirdly, convenience is a factor. Using a transformer is generally more convenient if the equipment may need to be moved in the future or if the existing electrical panel is easily accessible. Installing a separate service requires more extensive wiring and may involve more disruption to the building. However, a separate service provides a dedicated power source, which may be advantageous for sensitive equipment that requires a stable and reliable power supply. Here is a more detailed breakdown of the transformer option. When selecting a transformer, firstly determine the voltage requirements. Ensure that the transformer's primary voltage matches the available supply voltage, which in this case is 120/240 volts. The secondary voltage should match the equipment's required voltage, which is 120/208 volts. Secondly, determine the kVA rating. Calculate the total volt amps required by the equipment. This information is usually found on the equipment's nameplate. Add a safety margin, typically 25%, to account for inrush current and future load expansion. Select a transformer with a kVA rating that meets or exceeds this calculated value. Thirdly, consider the transformer type. There are different types of transformers available, such as dry-type transformers and liquid-filled transformers. Dry-type transformers are typically used indoors, while liquid-filled transformers are used outdoors or in specialized applications. Choose the appropriate type based on the installation environment and applicable codes. Fourthly, review the efficiency rating. Transformers are not 100% efficient, and some energy is lost in the form of heat. Look for transformers with high efficiency ratings to minimize energy waste and reduce operating costs. Fifthly, ensure proper installation. Install the transformer in a well-ventilated location to prevent overheating. Mount the transformer securely to a wall or floor, following the manufacturer's instructions. Connect the primary and secondary wiring according to the National Electrical Code, or NEC, and local codes. Provide overcurrent protection on both the primary and secondary sides of the transformer. And finally, have regular maintenance. Inspect the transformer regularly for signs of damage or overheating. Clean the transformer to remove dust and debris. Tighten all connections to ensure proper electrical contact. Consider the separate service option in more detail. Firstly, plan the service route. Determine the route for the new service drop from the utility pole to the electrical panel. Ensure that the route is clear of obstructions and complies with all applicable clearances and regulations. Secondly, obtain necessary permits. Obtain all necessary permits from the local utility company and building department before starting any work. This may involve submitting plans and specifications for review. Thirdly, install the service drop. Have the utility company install the new service drop from the utility pole to the building. This typically involves running overhead or underground conductors to a service entrance point on the building. Fourthly, install the meter and panel. Install a new meter and electrical panel at the service entrance point. The panel should be sized to accommodate the equipment's load requirements and any future expansion. Fifthly, connect the wiring. Wire the equipment directly to the new panel following the NEC and local codes. Use appropriately sized conductors and overcurrent protection devices. Sixthly, ground the system. Ensure that the electrical system is properly grounded to prevent electrical shock hazards. This typically involves connecting a grounding electrode conductor to ground rod or water pipe. And finally, inspect and test. Have a qualified electrician inspect and test the new electrical service to ensure that it is safe and functioning properly. This may involve performing voltage and current measurements, insulation resistance tests, and ground impedance tests. Let's now look into the safety considerations in greater detail. Firstly, grounding is essential. Proper grounding is critical to prevent electrical shock hazards. The grounding system provides a low impedance path for fault current to flow back to the source, causing the overcurrent protection device to trip and energize the circuit. Grounding should comply with NEC section 250. Secondly, overcurrent protection is needed. Overcurrent protection devices, such as fuses and circuit breakers, protect the electrical system from overloads and short circuits. These devices should be sized according to the ampacity of the conductors they protect. Overcurrent protection should comply with NEC section 240. Thirdly, wire sizing matters. Conductors must be sized appropriately to carry the intended load current without overheating. The ampacity of a conductor is determined by its size, insulation type, and installation conditions. Wire sizing should comply with NEC section 310.15. Fourthly, clearances are important. Maintain adequate clearances around electrical equipment to prevent accidental contact and allow for proper ventilation. Clearances should comply with NEC section 110.26. Fifthly, lockout and tag out procedures are vital. When working on electrical equipment, always follow lockout and tag out procedures to prevent accidental energization. This involves disconnecting the power source, locking the disconnect switch in the off position, and attaching a tag indicating that the equipment is being worked on. Sixthly, use personal protective equipment or PPE. Wear appropriate PPE such as insulated gloves, safety glasses, and arc-rated clothing when working on electrical equipment. PPE protects workers from electrical shock, arc flash, and other hazards. Seventhly, follow the NEC. Adhere to all applicable requirements of the National Electrical Code, or NEC. The NEC is a comprehensive set of standards for electrical installations. Finally, hire a qualified electrician. All electrical work should be performed by a qualified electrician who is familiar with local codes and safety standards. A qualified electrician has the knowledge, skills, and experience to perform electrical work safely and correctly. When deciding between using a transformer and installing a separate service, consider these points. For a transformer, the advantages include lower initial cost, easier installation, and flexibility. The disadvantages include lower efficiency, potential for voltage drop, and limited capacity. For a separate service, the advantages are higher capacity, better voltage regulation, and increased reliability. The disadvantages include higher initial cost, more complex installation, and longer lead time. Let's consider some specific applications. In a veterinary office, an X-ray machine requires a stable and reliable power supply. If the existing electrical system is already heavily loaded, installing a separate service may be the best option. However, if the X-ray machine is only used occasionally and the existing electrical system has sufficient capacity, using a transformer may be a more cost-effective solution. In a commercial building, a large piece of equipment, such as an industrial oven or a large air conditioning unit, may require a dedicated power source. Installing a separate service ensures that the equipment has sufficient capacity and does not overload the existing electrical system. In a residential setting, a small piece of equipment, such as a hot tub or a swimming pool pump, may require a 240-volt power supply. Using a transformer to step up the voltage from 120 volts to 240 volts may be a simpler and more cost-effective solution than running a new 240-volt circuit from the main electrical pile. Now let's explore some common issues and troubleshooting tips. If the equipment is not receiving the correct voltage, firstly check the transformer connections. Ensure that the primary and secondary wiring is properly connected and that all connections are tight. Secondly, check the transformer voltage taps. Some transformers have voltage taps that allow you to adjust the output voltage. Make sure that the taps are set to the correct voltage. Thirdly, check the supply voltage. Use a voltmeter to measure the voltage at the primary side of the transformer. Ensure that the supply voltage is within the transformer's input voltage range. Fourthly, check the load. Make sure that the equipment is not drawing more current than the transformer is rated for. Overloading the transformer can cause voltage drop and overheating. If the circuit breaker keeps tripping, firstly, check the circuit breaker size. Ensure that the circuit breaker is sized appropriately for the load. Secondly, check for shorts. Look for any signs of short circuits, such as damaged wiring or loose connections. Thirdly, check for overloads. Make sure that the equipment is not drawing more current than the circuit breaker is rated for. Fourthly, check for ground faults. Use a ground fault locator to identify any ground faults in the circuit. If the transformer is overheating, firstly, check the ventilation. Make sure that the transformer is installed in a well-ventilated location. Secondly, check the load. Make sure that the equipment is not drawing more current than the transformer is rated for. Thirdly, check for loose connections. Tighten all connections to ensure proper electrical contact. Fourthly, check for harmonics. Harmonics can cause transformers to overheat. Use a power quality analyzer to measure the harmonic content of the current. In conclusion, obtaining 120/208 single-phase power can be achieved through either using a transformer or installing a separate electrical service. The choice depends on factors such as cost, convenience, safety, and the specific requirements of the equipment being powered. Always consult with a qualified electrician to determine the most appropriate solution for a specific situation and to ensure that all electrical work is performed safely and in compliance with applicable codes and regulations. Remember, electrical work can be dangerous, and it is always best to leave it to the professionals. By understanding the options and considerations outlined here, you can make informed decisions about how to best obtain 120/208 single-phase power for equipment. Always prioritize safety and consult with qualified professionals to ensure a safe and reliable electrical installation. Before undertaking any electrical project, it's crucial to consult with local electrical codes and regulations. These codes provide specific guidelines and requirements for electrical installations, ensuring safety and compliance. Familiarizing yourself with these codes will help you make informed decisions and avoid potential hazards. Furthermore, selecting the right components is essential for a successful and safe electrical installation. Choose high-quality transformers, circuit breakers, wiring, and other components that meet or exceed industry standards. Using substandard components can compromise the safety and reliability of your electrical system. Regular maintenance is also vital for ensuring the long-term performance and safety of your electrical system. Schedule regular inspections and maintenance checks to identify and address any potential issues before they escalate. This proactive approach can help prevent costly repairs and ensure the continued safe operation of your electrical system. When working with electricity, always prioritize safety above all else. Follow all safety guidelines and procedures, and never take shortcuts or compromise on safety. Electricity can be dangerous, and it's essential to treat it with respect and caution. By adhering to these guidelines and working with qualified professionals, you can ensure safe, reliable, and code-compliant electrical installation.